Yep. Before starting my presentation, thank you all of you for attending our webinar, and I would like especially thank Copenhagen University for giving us this opportunity to share our results of our projects that we are doing. I'm working on a project that is supported by EU. Mainly, I'm working on tooth movement modeling project for orthodontics. Joint with it's a project joined with 3Shape and University of Copenhagen. As we all may know, the orthodontics attempts to correct malpositioned teeth or jaw. And the treatment begins with a malocclusion, and an orthodontist try to get an intraoral scan from the current stage of the patient and designs an ideal case for the patient. And by designing that well-positioned teeth in the patient's jaw, they prepare a treatment plan for that patient, which includes several subsetups, and each of these subsetups have designed based on the target position of the teeth that the orthodontist plans to move the teeth towards that one. And each of these subsetups depends on the efficiency of the previous subsetups in the case that it can be moved properly to the previous target position or not. But in general, tooth movement can be dependent to different factors, and it can be different from one patient to another patient. It can be dependent to the magnitude of the applied load, bone and tooth supporting complex, physiological factor, and some metabolism factor that can affect bone remodeling process. All of these factors can be, some of these factors can be taken into account in the finite element analysis in order to have a better prediction of the tooth movement. So this has motivated us to develop a patient-specific model of human jaw using finite element analysis to investigate tooth movement variations across different patients. So here I want to show short demo of the aligner treatments. Here on the left side, you can see the aligner that is the retainer model. This model perfectly fits the teeth of the patient. So there isn't any penetration between the aligner and the patient's jaw. But in the middle model, we can see the aligner that is designed for the next subsetup. And mainly this aligner has been designed in order to move the teeth toward the target position. And you can see the penetrations between the aligner and the teeth in these regions. So what we are doing here is to provide some framework, and which is based on the finite element analysis. And by running the simulations, we want to see that if the aligners can effectively move the teeth toward their target positions. Here, I will show the demo of our simulation results. You can see that the penetrated regions, they get smaller while the simulation is running, and the teeth are pushed to the target position of the teeth as planned in the treatment plans. And if we hide the aligner, we can see that how the teeth are moving in the simulation. And mainly, it is important to know that if the movement of the teeth have been efficiently occurred, or could we achieve our plans. Here I'm magnifying the displacement of the teeth so that you can easily see that how the teeth are moving based on our plans. But we are going to more work on this project because it's a sub-project of our work, and but I won't go into details about the precision of the teeth that are moving, if they are moving properly or not. So in my next few slides, I will explain that how we are preparing these biomechanical models of patients' jaws. Here you can see 3 examples of our patients that we have randomly selected. If we take a closer look to our biomechanical models, we can see that there is a soft tissue between the tooth and the bone that connects tooth to the alveolar bone, which is called periodontal ligament or PDL layer. This layer acts like a shock absorber and plays an important role in exerting the applied load and also the stress into the bone, which causes the bone remodeling process, and as a result, the tooth moves inside the bone. After preparing the required geometries for each patient, we also compute the volumetric meshes using TechGen software. And after that, using some 4 quality measurements, we ensure that our tetrahedrons that we are using in our simulations, they have high qualities, and our simulation results are reliable and they're not affected by badly shaped tetrahedrons. After computing the volumetric meshes, we set up the finite element problem. Here, we define the boundary conditions. For example, we fix all nodes at the bottom part of the bone. And we define the tight contact in the PDL bone and PDL tooth interfaces. Also, we define the loading condition. It could be based on, for example, it could be based on the pressure load that is applied to the surface of the tooth, or it could be based on the aligner that we are using. It totally depends on the treatment that we want to model in the real world. And finally, we define different material models, such as hyperelastic material model for the soft tissue in between the bone and tooth, so that we can model the nonlinear behavior of the PDL layer properly. And it will help us to predict the tooth movements in a more realistic way. Here, we have a short demo of how we are applying the forces in order to mimic the uncontrolled tipping scenario by applying the forces perpendicular to the surface of the teeth simultaneously. We can see that when we are applying the load to the surface of the teeth, there are some stress concentrations around the cervical region of the bone. And also there are some stress bridge. And also there are some stress bridge in front of the bone as well. This means that when we are applying a force to a tooth, it not only affects its surrounding circuits, but also it affects the neighboring regions of the bone as well. Also, here you can see the tooth movements, the displacement of the teeth using the red arrows here. And as you can see in this patient, for example, the left incisor have more movement compared to the right incisor. So this means that we need to, even if in a single patient, for the same teeth, we would have different kind of movements. So we need to, for each tooth, we need to take the some kind of clinical biomarkers that can help us to predict the movement of the teeth properly. So in order to verify our models and make sure that our models are predicting the real world and they're reliable, first we numerically verified our model using mesh convergence study and also parameter sensitivity analysis. So in the mesh convergence study for an identical scenario, that the scenario is, I'm presenting the utilized scenario here on the right side. We are trying to increase the number of the elements with a factor of 2 iteratively. And while doing this process, we are trying to see that how the stress distribution and stress concentrations are changing in our simulation results, and if our simulation results are dependent to the size of the elements. And then we use the finest elements in order to ensure that our results are reliable and are not affected with the mesh resolution. But if we compare the geometries of different patients, we can see that the bone geometries of the patients are changing, and also we can see a high differences in the shape of the teeth geometries as well. And there are some variations in the roots and crown sizes as well. And in order to take these variations into account, we need to somehow provide a generic model that can consider these variations as well and help us to better predict the movement of the teeth. So our pipeline can be summarized as follows. First, we obtain the patient-specific geometries, and then we set up the finite element problem for the patient. But we need to conduct this process for several patients. And finally, by adapting the biomechanical models of different patients, using some clinical biomarkers and statistical models, we prepare a generic model. So if I want to show an example that how we can provide a generic model, we can set up a parametric model by using our simulation results of several patients, and also using the loading conditions that we have used in our simulations, and also consider the biomarkers such as crown height, root lengths, and in general their sizes. Because we need to consider these biomarkers because these biomarkers can help us to compensate for these variations between the different patients' geometries and have a better prediction of the tooth movements. And later, this trained model can be used in order to predict the model, and we can use for this model to predict the movement of the teeth of a new patient by using the biomarker of that patient and also using the loading condition as an input, and we can get the translation, rotation, and the rotation degree as the output of our model. So to conclude my presentation, we have developed multi-patient finite element models, and we are trying to consider the any available tendencies across different patients and subjects. Although it is possible to prepare any patient-specific or subject-specific finite element models, but it is a challenging process in order to generalize these models for a larger group of the patients. And in order to conduct such a generalized model, one can try to automate the whole pipeline of CBCT segmentation and also preparing the finite element analysis models. And also one can develop a framework that can learn these generic models and try to predict the results of the finite element models without any requirement for developing these models. This sums up my presentation. Thank you for your attention. And if you have any questions, I would be happy to answer them.